So welcome to the 34th lecture, and in this lecture I'll discuss the biasing of PN junction diode with you. Now in the last lecture I discussed PN junction diode with you, and I told you that this PN junction diode, if you remember, this called a PN junction diode, is a two layer. There are two layers in it. One is called the P and the other is called N layer. This is having acting as a P type semiconductor, this is acting as a N type semiconductor, and of course P type semiconductor will have acceptor ions. Of course it will have acceptor ions. This is formed by adding the acceptor impurity. It will have negative acceptor ions, and the majority charge carriers are holes here. The majority charge carriers are holes. Along with these acceptor ions, along with the, no doubt you have these negative acceptor ions also, and in case of your N side you will have majority of electrons. Now at the same time I told you that near the junction you have these negative ions. Near the junction you have these negative ions and these positive donor ions. These are positive donor ions here, and these are negative acceptor ions. Now these ions, these immobile ions, they obstruct they simply act as a barrier. They are acting as a barrier as a flow of these electrons or holes, or they are acting as a barrier for them to cross the junction, for these mobile charges to cross the junction. And I told you that a potential is developed here, internal potential is developed here, and this potential is called a barrier potential. Is called a barrier potential, or in many books, or it is also called a built-in potential. Built-in potential, a potential that is built inside this semiconductor itself, within this diode itself. I told you that this is called cathode and this is called anode. Positive, this is called anode and this is called cathode, and this region is called a space charge region or depletion layer. This layer is called, up to this point I have discussed with you, I am repeating this. This is called a depletion layer, or this region is called the space charge region. And under this condition, just see these symbol also I told you that this is a symbol of a diode. This is representing anode and this is representing a cathode. This is anode and this is cathode. Now these are the two layers. This is called P layer and this layer is called the N layer. Now as far as these terminals are not connected to any battery, or I say that no potential is applied to either P layer or to N layer, this is called open circuit. This is called, we call this type of PN junction diode as this is open circuit. This is an open circuit. Now if I close this with the help of a battery, if I want to connect this to a battery, means a battery will have a positive terminal and a negative terminal, and it means some amount of voltage is applied, some amount of potential is applied to anode, and some amount of potential is applied to the cathode. So how potential is applied to the different layers of a semiconductor is called biasing. So it is providing potential. How to provide means potential or voltage. I can say it is the potential applied to diode layers. Or I can say that how this potential is applied to this diode layers based on this based on this, that how we are applying the potential on P layer or on the N layer. That defines the biasing of this, of a PN junction diode. And there are two types of biasing in a PN junction diode. One is called the forward bias. First is called the forward bias. Forward bias. And the second is called a reverse bias. Diode can be either forward biased or reverse bias. I'll discuss them one by one. What do you mean by forward bias and what do you mean by reverse bias? So let's discuss them. First, I'll come to forward biasing. First part is forward bias. Forward bias. Forward bias is when anode is at higher potential. I'm sorry, not what. When anode is at higher potential than cathode. When anode is at higher potential than the cathode, then the diode is said to be forward biased. Let me show it with the help of a, that is, if you have this diode here, if you have a diode here, and this is anode and this is cathode, if I make a battery like this, suppose I say that this is a 10 volt battery, just try to understand this, that suppose I say that this is a, I show it here, this is anode of course and this is cathode. I connect it to a battery here. I connect this to a battery here, and suppose I say this is a 10 volt battery. What does this mean? It is a 10 volt battery, means this is at 10 volt as compared to this is at 0 volt. This terminal at 0 volt and this is at 10 volt, means anode is at 10 volt and cathode is at 0 volt. This is cathode. Cathode is at 0 volt, so anode is at higher potential as compared to cathode. So when anode is at higher potential than cathode, then this is said to be forward bias. Now what actually happens in this forward bias? Let me explain this. See what will happen. Let me show it here. Under this forward bias conditions, say this is P layer and this is N layer here. This is P and this is N. What will happen under this condition? Of course, it is like this. It is connected here in this way. This will have majority of holes. This will have majority of holes. And of course, this N layer will have majority of electrons. But remember that here you have a depletion layer is already there. This depletion layer is already there. Now when I apply this here, this battery will supply electrons, and I can say this is positive and this is negative. This will supply electrons here, and naturally what will happen, or I can say that these holes will be repelled by the positive terminal of the battery and they'll cross the junction. But what will happen, look at the VI characteristics of this. If I draw the VI characteristic here for a forward bias, that is, if I apply this voltage V, and if the current flowing through this diode is suppose I, this is the applied voltage V here. Now what will happen under this condition? Look at this. Initially, till this barrier potential is there, till this barrier potential is here, I am applying here, up to this has to overcome this barrier potential, means these immobile charges either from this side or from this side, they are acting as an obstacle to the flow of these electrons or holes, or they are acting as an obstacle, as a barrier for these charge carriers to cross this junction. So up to this point, suppose I say that this barrier potential is VB. Up to this point VB, the current is approximately 0. Ideally it is 0. is approximately equal to 0, and once it has overcome this, the current increases exponentially. So this is the forward characteristics, and this voltage is called knee voltage. Many times this is also called the knee voltage. So first, this has to overcome this barrier potential. Until unless it does not overcome this barrier potential, this is approximately equal to 0. So this is your forward bias. This is how this diode acts as a forward bias. Once it has overcome this voltage, it acts as a closed switch. That is, I can show it like this, that this diode, when it is forward biased, look at the equivalent circuit of this. Of course, this diode will have some resistance, and suppose I say that I name this as forward resistance RF, where this RF, this R in suffix, this is F. This RF represents the resistance, the diode resistance, the resistance of this diode under forward bias condition. And once it has overcome this barrier potential, once it has, this is V that is applied here, once it has overcome this barrier potential, now it acts simply as a closed switch. It simply acts as a closed switch. Till then it was acting as a open switch, and now it acts as a closed switch. So this is how this diode is acting in a forward bias. So under forward bias condition, first of all, it has to overcome this barrier potential. Once it overcomes this barrier potential, then this current increases exponentially. That is the main difference between a resistance. A simple, it is not a linear, this current is increasing exponentially here. And of course, it will have some resistance. This diode can offer some resistance, and that value of resistance I can find from here. A static resistance can be, I can say that this voltage upon this current, V upon I, at this point, it is your static resistance. If I have to find a dynamic resistance, I can take any 2 points, that is dynamic resistance of this. So this is about forward bias. Let's talk about the reverse bias. What happens under reverse bias condition, and what is the definition of this reverse bias? Just the reverse of this, I say that when anode is at lower potential, when anode is at lower potential than cathode, Now under this condition, it is acting as a open switch, as a closed switch. This acts as a closed switch. Of course, if it is having some forward resistance, that will be there. Ideally, we assume that there is no forward resistance also. So now let's come to reverse bias. When anode is at lower potential as compared to cathode, what do I mean by this? That is, here I say that the current flowing here is, this is I. Now what will happen? Now this anode is at lower potential, means I put it at 0 potential and this at some potential V. That is, if I apply a battery of V volt here, if I apply a battery of, say this is V here, it means this is, say suppose this is 10 volt. So this point is at 10 volt and this point is at 0. So cathode is at higher potential, or I say that anode is at lower potential as compared to cathode. Now what happens under this condition? Look at this. I'll try to explain this with the help of this. Say this is P and this is N here. This is reverse bias. Reverse bias means this is at lower potential and this is at higher potential. Now naturally that this P layer will have majority of, this is a barrier potential already, I'm showing it here, and this will have majority of electrons. Of course, here you will have negative ions. Here you will have negative ions also. Don't forget about these ions. You have these ions. And here you have the positive ions, along with these electrons and holes here. Now what will happen when this is in this format? When this is in this format, what one type of explanation I'm telling you, that these holes will be attracted by the negative terminal of the battery, and these electrons will be attracted by the positive terminal of the battery. Now, when this electron is shifted from here, leaving behind only this ion, positive ion, this donor ion. Similarly, when this hole moves this side, leaving behind only this negative acceptor ion, immobile ions. What is happening? It means that this depletion layer width is increasing. As I keep on, if I keep on increasing this depletion layer width will increase by the application of this. This depletion layer width will increase, and of course no current will flow in the external circuit. And ideally it is acting as an open switch. But apart from this, as I told you, that you have some minority charge carriers here. These are the minority charge carriers, means electrons are the minority charge carriers in p layer and holes are the minority charge carriers in this layer. Now what will happen? Of course a current will flow. A current will flow because of these minority charge carriers, and that current is known as the leakage current. I am showing this reverse characteristics here only. That is a small current, that is a leakage current will flow here. This current, a very small current, that is called leakage current, a very small current. So a kind of current that flows here in this case is a leakage current, or we call it reverse saturation current. Leakage current. This leakage current is due to what? It is due to the minority charges. Is due to minority charges. This p layer will have electrons as a minority charge, n layer will have holes as a minority charge. Of course they will cross the junction. Now try to understand this. If I keep on increasing this, voltage, that is if I am increasing this reverse voltage, here, what will happen? A stage will come in such a way that if I keep on increasing this, what will happen? That the kinetic energy of these electrons will increase and they'll break the covalent bond. They'll break the covalent bonds here. And accordingly what will happen if the covalent bond is broken? If this V increases, remember that, if this V increases, implies that what will happen? The kinetic energy of the charge carrier will increase. This implies that covalent bond breaks. Covalent bond breaks. If covalent bond breaks, what does it mean? That electrons and holes will be generated. Electrons as well as holes will be generated. Here, these are covalent bonds. I told you that you have various covalent bonds here. This silicon in this way. Covalent bonds are there. Along with your, say, phosphorus is here and all these things, indium is here. So these covalent bonds will break. If covalent bond breaks, electron and hole will be generated. Further, these electron and hole will break another covalent bond, and further these electron holes, further more electrons and holes are generated. A number of electrons and holes are generated, and this is called the avalanche of charge. A large amount of charge. And whenever there is a large amount of charge, it means a very high current will flow. Under this condition, if I keep on increasing this, a stage will come that a very high current will flow. And the potential at which, or the voltage at which this occurs, is called the breakdown voltage. This is called the breakdown voltage. Remember that this will increase the junction temperature. This increases the junction temperature and the diode may damage. So one should avoid this breakdown, whatever this breakdown voltage is. In all the specifications it is mentioned that what is the peak inverse voltage. This is also called a peak inverse voltage. That is, under the inverse condition, what is the maximum allowable voltage that must be applied to this diode. However, a small leakage current is flowing here. This current is the leakage current. So this is your biasing of the diode as a forward bias and reverse bias. Ideally, If I talk about ideally, under this condition, this diode is acting as a open switch. Under reverse bias condition, this diode, it acts as a open switch. In forward bias, the diode acts as closed switch. Means ideally it is offering zero resistance. Ideally it is zero resistance, and in reverse bias it acts as a open switch. That is, ideally it is offering infinite resistance, but practically it has a resistance of several mega ohms. In this case it has some resistance of few ohms. So this is all about, for the time being, for about the biasing of PN junction diode, that is, it is reverse bias or forward bias. So I'll stop here at this point. Thanks for the time being.